So far we've defined the natural logarithm and the natural exponential, which are inverses of each other, and we've derived rules for these functions, limits, derivatives, and antiderivatives. And in lecture 4 we're going to generalize these functions and also the rules associated to them. For any positive number a, we make a definition: a to the x is e to the x times ln of a. And note that this only works for positive a, since the natural logarithm is only defined for positive number a. And if we apply the natural logarithm to both sides of this equation, we get the natural log of a to the x is the natural log of the right hand side, which is just x times ln of a. We get the usual laws of exponents, which we can derive from the same laws for e to the x. For example, a to the x plus y by definition is e to the x plus y times ln of a, and we can break up that power and then separate the e to the x times ln of a and e to the y times ln of a using the laws we've already defined for the natural exponential, and then convert back to a to the x times a to the y. And the other rules follow in a similar manner. And we can also derive a rule for differentiation. By definition, a to the x is e to the x times ln of a, so the derivative of a to the x with respect to x is the derivative of this function, which is just e to the x times ln of a times the derivative of the power here, but ln of a is just a constant, so the derivative of that is ln of a, and so we get that the derivative of this entire thing is ln of a times the thing itself, which is a to the x. And we can also use the chain rule in conjunction with this rule in order to get a derivative for a to the gx. For example, if I wanted to find the derivative of 5 to the x cubed plus 2x, instead of memorizing this complex rule, it's best just to convert this to the form e to the hx and use the chain rule along with the derivative of e to the x. So we have 5 to the x cubed plus 2x is e to the x cubed plus 2x times ln of 5. And using the chain rule, we get the derivative of that is itself times the derivative of the power. And because ln of 5 is a constant, then the derivative of the power is ln of 5 times 3x squared plus 2, and this gives us our derivative right here. We can draw a picture of the graph of y equals a to the x, and of course this depends on the value of a. And so we're going to split our analysis into two cases. Case 1 is when a is between 0 and 1, and case 2 is when a is bigger than 1. And when a is between 0 and 1, we can apply our techniques from Calc 1 to find out what the graph looks like. First of all, the y-intercept is a to the 0, which is just really e to the 0, which is 1. And there's no x-intercept because a to the x is e to the x times ln of a, and it's always positive, so it never takes the value 0. The slope of this function is the derivative, which is a to the x times ln of a, and here, because a is between 0 and 1, ln of a is negative, and the slope is negative, so we find this function is sloping downwards from left to right. You'll also see that to the left of the y-axis, these curves are steeper for smaller values of a. The graph is going to be concave up, because if I take the second derivative, I get a to the x times ln of a squared, which is always going to be a positive number. And then as x approaches infinity, ln of a is a negative number, x is positive, and x times ln of a approaches negative infinity. So a to the x, which is e to the x times ln of a, approaches e to the negative infinity, which it approaches 0. And as x tends to negative infinity, x and ln a are both negative, so their product is positive, and e to the x times ln of a approaches e to the infinity, which tends towards infinity. So we get two limits. The limit as x tends to infinity of a to the x is 0, and the limit as x tends to negative infinity of a to the x is infinity, keeping in mind that a is between 0 and 1. For a bigger than 1, the graphs slope upwards. Again, the y-intercept is 1. There's never an x-intercept. And now the slope of the function is positive because the derivative is a to the x times ln of a, but ln of a is now a positive number, and so is a to the x, so the derivative is always positive. And again, we get the second derivative is positive, so it's still concave up. And larger values of a are going to give you a steeper curve to the right of the y-axis. As x approaches infinity, the graph will approach infinity, or a to the x will approach infinity, and as x approaches negative infinity, then a to the x will approach 0. So for a greater than 1, the limit as x tends to infinity of a to the x is infinity, and the limit as x tends to negative infinity of a to the x is 0. We will take note of our power rule, which you may now find confusing because we have 4 different types of power functions. So if we just have a function of the form a to the b with no x's whatsoever in it, its derivative has to be 0. And we knew in Calc 1 that if we have a function of the form f of x to the b, we can use the power rule and the chain rule, and its derivative is b times f of x to the b minus 1 times f prime of x. In this lecture, we just saw that the derivative with respect to x of a to the gx is equal to a to the gx times the derivative of g of x times ln of a. And now lastly, we'll do some examples in class of functions of this form, f of x to the power of g of x. And for these we have 2 options. We can either use logarithmic differentiation or rewrite the function in this form and use our techniques from last class. It's the derivative of the power here times the function itself, e to the gx times ln of f of x. So in class we'll do some examples that look like this, using perhaps logarithmic differentiation. Also, if you want to calculate limits of functions that look like this, it's a very good idea to convert them to this form and then use our techniques from the previous lecture to calculate the limit. Since this function f of x equals a to the x is either always increasing or always decreasing, it must have an inverse. And we call that inverse log to the base a of x. And by the general properties of inverse functions, we must have log to the base a of x is y is the same as saying that a to the y equals x. And we must also have that a to the log to the base a of x is x, and log to the base a of a to the x is also x. it's not hard to show that in fact log to the base a of x is just a constant multiple of the natural logarithm function. So to prove this formula, which is called the change of base formula, suppose y equals log to the base a of x. Then since a to the x is the inverse of log to the base a of x, we have a to the y equals x. And then if we take the natural logarithm of both sides, we get y times ln of a equals ln of x. And now dividing across by ln of a gives us y equals ln of x over ln of a, but y is log to the base a of x. So this gives us our change of base formula. This means that because log to the base a of x is just a constant multiple of the natural logarithm, it has these same properties. Log to the base a of x times y is log to the base a of x plus log to the base a of y, etc., etc. In general, in order to calculate derivatives, limits, and integrals involving log to the base a of x, it's best to convert this function to the form of the natural logarithm using this change of base formula. And we have the most commonly used logarithm functions are log to the base 10 and log to the base e, which is just the natural logarithm. We can also derive the derivative using the change of base formula, and you see here that the derivative of log to the base a of x is the derivative of the natural log divided by log to the base a, so it's 1 over x times ln of a. And you can also use the chain rule along with that to derive another formula for log to the base a of g of x. We'll also look at a very special limit. E is the limit as x goes to 0 of 1 plus x to the 1 over x. Or we can rephrase that as e is the limit as y tends to infinity of 1 plus 1 over y to the y. Or if we're just restricting our attention to large integers, we have e is the limit as n goes to infinity of 1 plus 1 over n to the power of n. So this formula manifests itself in 3 different ways, but essentially it's all the same formula. And how would we find that formula? Well, we find that by looking at the derivative of the natural logarithm at x equals 1. So we know that that derivative of the natural logarithm of x is 1 over x, and so the derivative at 1 is 1. And by the definition of derivative, that's also equal to the limit as x goes to 0 of ln of 1 plus x minus ln of 1, which is 0 over x. And that's the limit as x goes to 0 of ln of 1 plus x to the 1 over x. So we have an equation. That limit equals 1. And now I can apply the exponential function to both sides of that equation. When I apply the exponential function to the left, we see what happens here on this line. I get e to the limit is equal to the limit of e to the ln of 1 plus x to the 1 over x. That's because e is a continuous function, and I can interchange it with the limit. And now the e and the ln disappear, and I'm left with the limit as x goes to 0 of 1 plus x to the 1 over x when I apply the exponential to the left. And of course, when I apply the exponential to the right, I just get e to the 1. So that gives me this formula: e equals the limit as x goes to 0 of 1 plus x to the 1 over x. So we'll look at variations of that limit in class. Here we have a picture generated by Mathematica of the points n and 1 plus 1 over n to the n as n gets very large. And according to the limit on the previous page, the y values on this graph should approach e as n tends to infinity. And we see indeed that that is exactly what's happening.